This is a joint work with my advisor Yanxi Liu and as part of my PhD thesis at Penn State. Mathematically, a symmetry G of a set S is defined as a transformation G acts on S and keeps S setwise invariant. The two common types of symmetry are reflection symmetry, where one side is reflected with respect to an axis to the other side, and rotation symmetry, where G rotates S around a rotation center at a fixed angle, while S remains invariant to a set. We live in a 3D world, and photos are 2D projections of this 3D world. Thus, symmetries in a photo are an inherently ill-defined problem. For example, does this face have bilateral symmetry? Now it does in a 2D plane. Now it has an out-of-plane reflection. What about now? 3D symmetry leads to a dilemma for projected 2D symmetries. Mathematically, the invariant property implied by the definition of planar reflection symmetry requires that the two sides of a reflection axis are exactly the same, while human perception sometimes states otherwise. This is an example of a human perception or perceived reflection symmetry at a semantic level, the two individuals looking down at their phones, respectively. This poses a dilemma on 2D reflection symmetry. On the same image, this is an example of a human perceived out-of-plane reflection symmetry of a human face. Even on the profile of a 3D face, a reflection symmetry axis is identified. An example of a human perceived rotation symmetry center, regardless that half the mirror is missing. For survival, many biological systems, such as bees, dolphins, sharks, and pigeons, evolved to have the ability to recognize symmetry in the wild. Sharks have been trained to identify symmetric elements in these stimuli images. A recent cognitive study from our lab, in collaboration with Stanford, shows that human brains have significant responses to rotational symmetries and regular textures at V3 and higher regions in the visual pathway. These facts suggest that symmetry is an important mid-level visual cue that helps us understand the 3D world around us, but has not been fully explored in computer vision. Given the success of CNNs in computer vision, we are interested in finding out whether a CNN can be trained to perceive real-world symmetries like a human, and to help understand the concept of symmetry can be distilled by a neural network, hopefully. Object recognition and symmetry detection differs in some fundamental manner. Usually, objects in the same class share some color, texture, or shape features. For the same symmetry class, however, none of these might be in common except for self-symmetry of the two sides of the reflection symmetry, for example. In our previous work, we developed a method for collecting human symmetry perception data using crowdsourcing, and a clustering method to automatically find the consensus of all labels. To our surprise, regardless of variance in human symmetry tasks or label, they consistently converge to a few prominent symmetries. In this work, we convolve a Gaussian kernel with the sparse symmetry labels that turn them into dense n-by-n matrices for training. In our data set, about 1,200 COCO images are labeled by more than 400 human subjects. On average, about 29 labelers per image, 9 labels, symmetries per image, and 1,100 total labels. Among those, about 80% of the symmetries people agree on. We trained 2 networks based on Deep Lab version 2. A VGG-based network called SymVGG and a ResNet-based network called SymResNet. For training, we use an 80-20 split of the data. Here are some examples of results on our COCO dataset. Out-of-plane reflection symmetries are picked up from both the dog's faces and the windshield in the background. The slightly curved giraffe neck is captured even though the texture is not symmetric. We then tested Sym-NETs on previous symmetry competition data sets to see if this network generalizes onto other data sets. Sym-NETs can still find dominant symmetries within the image, but it can also find unlabeled lesser symmetries, such as the horizontal symmetry in the tail of the cat. On this building facade, reflection symmetries of the window and doorway are detected. This is a rotation symmetry results on our data set. The round circles are rotation symmetry centers. The occluded rotation symmetry of a half peach is even detected here. Even the sole of one of the elephant's foot is captured as a rotation symmetry. And so is the sign of the elephant in the background. The partial occluded rotation symmetry center of the lid is detected. So is the half pizza. But the transparent top of the glass is missing. But in this photo, the rotation symmetry center of the top of the glass is actually found. When we quantitatively evaluate on both COCO and previous symmetry competition datasets, the Sym-NET significantly outperforms all state-of-the-art computer vision algorithms evaluated. The dotted lines show the performance of Sym-NETs on those prominent symmetries only, each of which is labeled by more than 20 human subjects. Interestingly, other performances decrease on the most prominent symmetries, while ours increase. By adding random noise to one side of the reflection symmetry axis, we stress test the breaking point or asymmetric tolerance of the Sym-NETs on a common object and an unusual object, respectively. By using some photos with challenging symmetries, we visualize the activations at each layer to better understand how the networks work. At first, edge features are extracted, then the eyes of the cat become more prominent, now the wheels, and then prominent symmetries are found. Now the activations are inverted, the final symmetries are extracted. These images show that for reflection symmetry, the color and shading cues fade away at deeper layers. For rotation symmetry, local cues contribute more to rotation centers. Sym-NET's outcome seems to be affected only slightly by different orientations in the input photo, as shown here. We have developed two types of tools. Symmetry captures like a shield that protects us from bots, while Sym-NETs function like a spear to mimic human symmetry perception. As an ancient Chinese proverb goes, a merchant claims to have the best shield and the best spear. A person asks, what if you use your own spear to attack your own shield? Indeed, we are in a similar situation, and this is a question for us to answer as well. In summary, we've experimented with the first deep learning networks, Sym-NETs, for capturing human perception of real-world symmetries. Its performance has surpassed all state-of-the-art computer vision algorithms tested on multiple datasets. Our Sym-NETs demonstrated the ability to detect 3D symmetries, semantic symmetries, and occluded symmetries, and foreground and background objects as symmetries as well. Yet comparing with human perception, Sym-NETs still have a long way to go. Thank you for your time, and our poster ID is number 5.
Okay, we have time for some questions.
Thank you. One quick question. Do you expect some symmetric filters being learned in intermediate or early layers of the network?
Potentially. We looked through the network layers a little bit, but because we trained from, especially in early days, we took the weights from VGG networks, or pre-trained VGG and pre-trained resonant networks. We don't expect those to change that much. But for the later layers, like where the semantic information is coming out, and where I think actually, and where we train from random from about the fully connected layers, then yes, I think at that point, there's going to be some symmetric labels, some symmetric filters, such as, if we look at here, as we go through, but as we went through if you look at the activations at some of the later layers, you can start seeing as soon as you get to the middle of the network, that's actually when the real symmetries are being extracted. So first that's to pull out the features and then find the symmetries in the features themselves. Thank you for the question.
Okay. Are there any other questions?
Right there.
Oh, go ahead. There's a microphone in the middle of the aisle.
Thank you. I just wanted to ask about the rotational symmetries. So in the beginning, you showed the example with the triangle, and that's symmetric on 60 degrees rotations, or 120 degrees rotation. And but in all other examples you showed, it's always a circle that has rotational symmetry. Is it just detecting circles, because circles are always rotational, has rotational symmetry? Because it's not related to some specific angle. Like everything else seems to be horizontal, like some symmetry on a line, and circles are always rotationally symmetric. So it could be just a circle detector.
It could be, but then it wouldn't be able to find partial circles, such as the pizza here. The half occluded, yeah, there we go. The half occluded pizza would be hard to find because then it's only finding half a circle. And then also, say like the half a peach would be harder to find. So where occlusion happens, it still has to know a little bit more about it. But you're right, according to circles, it can't really be out of plane because of that, but it can be occluded. So for the peach here, even though it's semicircular around right here, it still needs to learn a little bit more about where the actual rotation is. Yeah, and also, thank you for my collaborator. And also the sign itself is not really symmetric as well, but it's still getting picked up, or rotationally symmetric because it's semi-rotationally symmetric. And it's a rectangle. And I can zoom into it right here. So here you can see the actual sign itself, it's a rectangle around it, but it's still labeled as symmetry. Thank you for the question.
Okay, thanks. Let's thank the speaker again.